last section of the weak acid is doing the same type problem that we just did, which is calculating the concentration using quadratic formula this time. So we're basically going to be finding pH given the concentration and the Ka, but this time we got to use the quadratic. So here's the process, but I'm actually going to jump down here first. So how do you know if you need to use a quadratic or not? Well, the first answer is if you always use the quadratic, you will never go wrong. However, the quadratic, of course, is a little bit more work than the non-quadratic. But the answer comes down to this formula here, the HA, the initial concentration of the acid, divided by the Ka, and whether it's greater than 100 or less than 100. So if I go back to this slide here, and we just do this calculation real quick, that we know that we use the assumption on, and I take the 0.10 divided by the 1.7 times 10 to the minus fourth. So this is the HA concentration divided by Ka. And when I do that, I get 588. So this is greater than 100. So use the assumption, and the assumption is referring to ignore minus x. Okay, we saw that, and we saw the fact it didn't make a difference in the concentration, but this is why that is now. Okay, in the next problem that we're going to do, so let me come back here and go through the process real quick. The process is basically exactly the same. The difference is that I cannot now ignore the minus x. So I need to simplify it into the quadratic formula and solve for that, and then do the pH and the degrees of ionization. So that's going to be the step. Is I'm going to have a denominator that's going to have a minus x, and I'll show you that on the next slide. So here's the problem. So I have the chloroacetic acid, and it wants to know what is the hydronium ion concentration. It wants to know what's the pH. If my initial concentration of HC2H2O, ClO is 0.002 molar, and my Ka is 1.3 times 10 to the minus 3. So if I do the same calculation of HA divided by Ka, I get 0.002 divided by 1.3 times 10 to the minus 3, and I get 1.53. So 1.53 is definitely less than 100, so must use quadratic. Okay, if I don't use the quadratic, you're going to get the wrong answer. Okay, so same process. I'm going to write out my formula, C2H2ClO2 plus water goes to form C2H2ClO2 minus plus H3O plus. This is 0.002 molar. The water goes away. This is 0 and 0, and I didn't put this, but this is my I. My C is minus X, X, and X. So this time, because this is less than 100, I cannot mark out this minus X, is basically what this means. That's the really easy way to say that. So I write my Ka expression. So I have Ka is my C2H2 ClO2 times hydronium over HC2H2ClO2. So I have 1.3 times 10 to the minus 3. This is 0 plus x and 0 plus x, so it's x squared over 0.002 minus x. So I can't get rid of, I have to instead have the minus x here. So I multiply both sides by this denominator. So I have 1.3 times 10 to the minus 3 times 0.002 minus x is equal to x squared. I distribute through, so this is going to be 2.6 times 10 to the minus 6 minus 1.3 times 10 to the minus 3x is equal to x squared. I stated my personal preference is that my x squared term is always positive, or the a is always positive, so I'm going to move both of these things over this direction, so everything's going to go this way. So I end up with x squared plus 1.3 times 10 to the minus 3x minus 2.6 times 10 to the minus 6 is equal to 0. So here's my A, my B, and my C. So the equation is x is negative, it just doesn't like me today, is negative x plus or minus the square root of b squared. This is supposed to be negative b, sorry, b squared minus 4ac divided by 2a. So x is going to be equal to a negative 1.3 times 10 to the minus 3 plus or minus the square root of 1.3 times 10 to the minus 3 squared minus 4 times 1 times, I can't write that there, a negative 2.6 times 10 to the minus 6, so all of that wraps around there, divided by 2 times 1. Now I will tell you a little secret. Since x can never be a negative term, if this term right here is negative when I put it in here, because it's negative b, and b was positive in this case. So if my first term is negative, it's always going to be the plus. I don't have to worry about going back and doing it with a negative term there. And so when I do the quadratic formula of this, I get x is equal to 1.089 times 10 to the minus 3. Okay. So I have the pH, and that's my hydronium ion concentration. My pH is negative log of 1.089 times 10 to the minus 3, which was 2.96. Okay. And my degree of ionization, DOI, is the 1.0899 times 10 to the minus 3 divided by my initial concentration of 0.002, and that gives me 0.544, or if I do it in percentages, it's 54.4% ionized. That's the other way to think about it. Okay. Compare that to the last problem that we did, and it was only 4% ionized, so this is a much stronger acid than the previous problem. Now, you don't have, I want to show you this, but it's not something I expect you to do, and so I'm just basically going to tell you what the answer is. If I had ignored the minus x, I would have gotten my hydronium ion concentration would have been, I didn't actually do that ahead of time, so it would have been the square root of 0.002 times 1.3 e to the minus 3, or 2.6, would have been equal to 1.61 times 10 to the minus 3. So you can see that compare 1.089 compared to 1.61, but you even see it even greater in the pH. The pH would have become 2.79. And so even with a plus or minus 2% error, which is usually what most problems give you, those are not the same answers. This was 2.96 versus 2.79. So that's why I would get the wrong answer if I did the ignoring minus x. Now, however, if I go back and do the last problem that we did in the last video, using the quadratic, I would get very similar answers. And so you can always use the quadratic. If you don't want to have to use the quadratic, then you must do the HA over KA. So you must do this calculation. If it's less than 0, or less than 100, you have to do the quadratic. If it's greater than 0, you don't need to use the quadratic. And that is the end of this video.